Okay, another problem from Chapter 8, rotational equilibrium and rotational dynamics. So we've looked at the first two. Let's take a look at the third problem. This one doesn't seem to be as complex. But we'll step through it and see how it's solved. In this one, we've got a model airplane with a mass of 0.75 kilograms, and it's tethered by a wire so that it flies in a circle 30 meters in radius. The airplane engine provides the net thrust of 0.8 of a newton perpendicular to the tethering wire. So they're asking us for three parts of the problem. First, find the torque the net thrust produces about the center of the circle. Then find the angular acceleration of the airplane when it's in level flight. And then finally, find the linear acceleration of the airplane tangent to its flight path. So as you can see here, worked out, these don't seem to be as robust as some that you've seen in the past. So let's take a look at the first one. Find the torque the net thrust produces about the center of the circle. So in this case, what we're looking at for A is the torque as, again, force times the lever arm. What's the force? Well, that's at 0.8 of a newton perpendicular to the tethering wire. And the lever arm is our 30 meters. So it's a simple product then to multiply those two together, and we end up with 24 Newton meters of torque. B, then find the angular acceleration of the airplane when it's in level flight. This one, all we have to do is take the definition for angular acceleration as the torque tau divided by I. Okay, so we're going to look at the definition of I as the simple mass times the radius squared, make that conversion, and now we do have the mass, we have the radius, and we have now the torque from part A. So it's a matter then of product and quotient. And we end up with 0.0356 radians per second squared of angular acceleration. Now we want to solve for, in part C, the linear acceleration of the airplane tangent to its flight path. So now we go back to the definition of acceleration tangent, which would be a linear acceleration, is equal to the radius times the angular acceleration. The radius we have, 30 meters, and we just solved for the angular acceleration value, and we end up with 1.07 meters per second squared as the tangent. Okay, fairly simple.